So let's look at solving linear inequalities. So I want to do a comparison. Let's say we have 1 minus 2x equals 7, and 1 minus 2x is greater than 7. And how does solving an inequality compare with solving an equation? So, if I wanted to solve this equation, what I would do is at first I want to get rid of that constant value of 1. So subtract 1 from both sides. Um, and with solving an inequality, same idea. I'm going to subtract 1 from both sides. That doesn't change the relationship. When you think about if this person has more money than this person, if you take $1 from each of them, the one that had more money is still going to have more money because they both reduced by the same amount. Same thing with an equation. If they're equal, you take $1 away from each of them, they're still equal. So next thing I would do is I would divide by that coefficient. I'd get x equals -3. So same idea here, divide by -2 here, and I'd get x is less than -3. So there's a little difference here. If you multiply or divide, when we say divide by -2, what we're meaning is multiply by a -1/2. It's just this is a shorthand way of saying that. Multiply or divide by a negative, the inequality flips. So what you're saying is I want the opposite of what I'm looking at when you multiply by a negative. So the opposite of a greater than is a less than. And you wanted to fancy that up in the set notation x such that that's true. And if you wanted to draw the number line, less than -3, so -3 less down that way. So that's how you can graph that stuff if you needed to. We're just solving it. So solving, your basic kind of linear inequalities, very much like solving an equation. Just keep in mind this rule: if you multiply or divide both sides of your expression by a negative, the inequality is going to flip. Now let's mention double inequalities, because that's something that really doesn't have a good, you don't see a lot with equations. So this would be something like -12 is less than 1 minus 2x, which is less than or equal to 9. Okay? So in this case, what I'm going to do here is, first of all, for this statement to be true, to be valid, if you don't look at the middle, it's got to be true. -12 is less than 9. Is that true? Yes. This is what we call the transitive property. If A is less than B and B is less than C, then that implies that A is less than C. So that statement has to be true. If you cover up that middle or you remove it, that the relationship on the outside too has to be consistent. So we see that's true here. So what I'm going to do is I'm going to focus on the part with my variable. So I'm looking at this middle part. I'm not really going to look at the outside parts. I'm going to work with them, but I'm not going to pay much attention to them for the moment. I'm going to say I want to get x by itself. So just like in the previous problem, I want to subtract 1. So this time I'm going to subtract 1 from all 3 parts. Again, that's keeping that relationship the same. And now again, I'm going to focus on the part with the x. And so I want to get rid of that -2. So just like before, I'm going to divide by -2. And I'm going to remember my rule. Because I divided by a negative here, these are negative. Right? Dividing by -2. That's what's important. Then what's going to happen is these negative divided by negative is going to be a positive. 13/2 is now greater than x, which is now greater than or equal to positive divided by -4. And again, if you kind of cover this up, you say, is 13/2 or 6.5, is that bigger than -4? Yeah, that's true. So this statement is true. Now, what I would probably do is, flip this around. So it's going the other way. You can think about what that would look like. And if you wanted to graph that, again, 4, 13 halves, equal negative 4, but it's got to be less than 13 halves, and then shade in between there. Okay, so that brings us to absolute value inequalities. Absolute value inequalities. Okay. So just like we were talking about absolute value equations, we're going to start with kind of a simple example here. Let's say the absolute value of some number is greater than 4. Now, let's consider what that means. So if I'm looking at the number line, I got 0. Remember, absolute value is the magnitude or the distance that number inside is from 0. So how big is the number? So this is saying you're more than 4 units away from 0. That means you could be down here below negative 4, or you could be up here above positive 4. So it's got to be more than 4 units from 0, left or right. That's what absolute value is indicating. So if I say, well, let me write this answer out, I'd say x is less than negative 4, or x is greater than 4. Now, if I look at this original statement, what I see is x less than 4. Oh, x less than 4, or sorry, I see x is greater than 4. I say, oh, x is greater than 4. That statement is true. And then I see a second statement, x is less than or equal to negative 4. So see how that inequality symbol and the sign of the number have both changed. So if you remember when we did equations, what happens is you'd get one equation that looked exactly the same as what was in, your problem, and then without the absolute value bars, and then you get a second one where you change the sign of the number on the other side. Well, we're seeing that happen, but we're also changing the sign of the inequality at the same time. Let's consider this second situation. What if I had a number and it was less than 4? How would that be different? So, again, I got 0, I got negative 4, I got positive 4. I want to be fewer spaces away than 4. So what that means is I want to be in this area right here. So one way I could describe that set is I could say I want numbers, x's, greater than negative 4, and also I want them to be less than positive 4. Now you can merge those together into a single statement, a double inequality, and say I want numbers between, physically between negative 4 and 4, but I want to kind of point out this first way because, again, what I'm seeing is, ignoring the absolute value symbol, what I'm seeing is there is one of these that looks exactly the same, inside part, outside part, and then another one where the inside part's the same, but we have the opposite inequality symbol and the opposite sign of the number. So, just like before, we got one that looks the same and then one where this is the outside part. Now, what's tricky about this is knowing when it's an and when it's an or. And so sometimes what people do is a little mnemonic device is they say, well, see this less than, it looks a little like an L. So this looks a little like land. So if I can remember one of these, so I remember this looks like a and, then this is the and this must be the or. Or maybe you think of this as like a door, I don't know. Looks like kind of a D, a door, I don't know. But, somehow you got to remember absolute value less than means and, absolute value greater than means or, trying to match that up. Now, remember, these are only for absolute value. So, like in this first few problems here we were solving, this isn't an or situation. This is just, solve it directly, get an answer. I want only numbers less than negative 3. When there's an absolute value, that's when you have two possibilities. You could be, the left direction or the right direction or whatever. And another thing to consider here is this is only, you can only make really this determination when the absolute value is by itself. So there's other things, then you got to work to get that by itself. So let's say I wanted to solve and graph, and I had 2 minus 3, absolute value of 1 minus, I'm using that way too much. Let's say 5x minus 4 is greater than negative 10. And I say, well, is that even possible? Whatever. Again, I got to get the absolute value by itself first. So first thing I want to do is get rid of this 2. So I'm going to subtract 2 from both sides. Negative 3, absolute value of 5x minus 4 is greater than negative 12. Now I want to get rid of this negative 3, so I'm going to divide by negative 3. So 5x minus 4 absolute value is now, because I divided by a negative, a less than positive 4. So now what I see is, oh, I have my little and, right? Little land, that was my little mnemonic device I was using. Land, all right? And I'm going to get one of these, 5x minus 4. That's going to look exactly the same as what I have here. And I'm going to get another one where the inside part's going to stay the same, but now the inequality symbol is going to change and the numbers on the outside is going to change. I'm going to work these two problems out. So I'm going to add, getting ahead of myself, add 4 to both sides. And get 8, and then divide by 5. So x is less than 8/5, and add 4. 5x is greater than 0, divide by 5. And notice my inequality symbols aren't changing because I'm dividing by a positive 5. They only switch when you divide by a negative. 0 divided by 5 is 0. So I want numbers less than 8/5, and I want numbers greater than 0. So what that means is my set of numbers is going to be between 0 and 8/5. Now, just to verify that, if I look at this first relationship, I want my number to be less than 8/5. Well, that's what this is saying. I want my numbers less than 8/5. So that's a true statement from what I got here. And then if I look at my second set of numbers, I want numbers bigger than 0. Or in other words, if x is bigger than 0, that means 0 is smaller than x. So this part of my statement is true as well. So both parts of my statement are true, and they're combined into this one statement. And then if I want to draw the graph, on the graph, what I'm looking at is exactly numbers between 0 and 8/5. There's my graph. Again, neither in this particular case are being included, but if this had been, started off with it or equal to, then both ends would be included here. All right, so last thing I want to mention is a few special cases. So let's say I'm going to keep this kind of simple. X minus 3 is greater than negative 2. X minus 3 is less than negative 2. X minus 3 is greater than or equal to 0. X minus 3 is less than or equal to 0. X minus 3 is greater than 0. X minus 3 is less than 0. Okay? So my claim is on all of these, I can make the determination of what the answer is without really doing any work or minimum work that I need to. This first one, the answer to this is an interval notation from a negative infinity to a positive. In other words, all real numbers, right? The second one is no solution. Or you could use this symbol as like the empty set symbol, or you can use that for the null set. Again, no solution. That's what all that stuff means. This one, again, all real numbers. use this notation, you can. X such that X is an element of the real numbers. This one, X equals a number 3. That's it. That's the answer. This one, X does not equal the number 3. And then this one is, again, no solution, or if you prefer, you can use one of those other ways of doing it, empty set or the null set. So why are these the answer? How do I know these without doing any work here? So when you do an absolute value and you plug numbers in here and you do a calculation, your answer is never going to be negative. It's going to be 0 or it's going to be positive, so 0 or bigger. So in that case, whatever number you plug in here and you do this calculation on the left, this answer is always going to be greater than -2, because the smallest it can be is 0, and 0 is bigger than -2, and then it's going to get bigger. So it's going to stay bigger than -2. Now you can't get -1 or -0.5 or something, but no matter what you plug in here, this calculation will give you a true statement. So this is all real numbers. Now, if you were to work it out or something, this is going to be an OR situation, and you're probably going to get something that looks like this. You know, remember we talked about that in that other video, ORs, if they're going in a different direction, that covers everybody. This one, on the other hand, you know, you're looking, the types of numbers that are less than -2 are only negative numbers. And since an absolute value you can't calculate to be negative, it's not going to work. So if you did work it out, you'd probably get something like this, and this is going to be an and you're going to get stuff going that way, and you're not going to get any overlap. So again, in that other video, we talked about how that could happen. This one, well, you can get 0 if you put 3 in there. That would give you 0, so I could equal 0. And then no matter what other number you plug in here, you're always going to get something that's positive. Positive number is always bigger than 0. So no matter what you plug in here, it's always going to be at least 0, and then probably most of the time it's going to be bigger than 0. So, you know, again, all real numbers. Now in this one, there's two possibilities. You could be less than 0 or equal to 0. Well, the only types of numbers that are less than 0 are negatives. So, you know, that is not actually possible. I can't be less than 0. But I have that option of being equal to 0. So what I need to do is ask myself, what number could I replace x with to make this 0? And that answer would be 3. So 3 is the only number that satisfies this expression. Now, if I look at this one, this is kind of like the reverse of that. Now I'm looking for numbers bigger than 0 or positive, but I don't want it to be equal to 0. So, you know, since no matter what you plug in here, you're going to get a positive unless you plug in the number 3, then that number is not going to be positive. So I guess here, let me real quick kind of, this would be an OR. You'd have a solid dot. You go that way and that way. Well, that would cover everybody. This one, this would be an and it would be like that same exact thing. You got a solid dot here, and you're going that way, but since, you know, and means overlap, the only place that overlap is there. This one would be an OR, but now you'd have an open circle at 3, and you go that way, so it would be everybody but 3. That's what we're saying here. When we're saying x cannot be 3, it's everybody but 3. And then this one is, you know, kind of the same idea, except this is an and so now, again, they're going in different directions. They're not overlapping, and they don't even have 3 in common because 3 doesn't actually work. So that's why this is no solution. You know, you're looking for numbers less than 0. Well, those are only negatives, and absolute value can't ever be negative. So there's some, you could work these out, and like I said, you'd get these kind of weird situations. You'd have to know whether it's an and or an or. It would make a difference. But if you kind of think about it and you just kind of step back and say, okay, what is really going on here? You can figure out these problems without doing all the work we just did. Now, these are only special cases, and normally, you know, like in this other example, you know, you just got to work it out and see what you get for the answers.